I believe this will be the last video. Rose curve, cosine of 3 theta. You're just supposed to know that the graph looks like this. Goes around like this, and in the matter of pi radians, you get a graph that looks like that. Really, it should be where. Add a little something to this. The line, this will be really helpful to you later on, but the line theta equals pi over 6 is tangent to this graph. Okay, right there at the pole. The line theta equals pi over 2 is also tangent at the pole. And then you have this line here where I didn't do a very good job drawing that, but the line theta equals 7 pi over 6 is also tangent to this graph at the pole. Okay, and then we have the graph of sine of 2 theta. Well, r equals sine of 2 theta. Notice that when the coefficient of the theta is odd, you have the same number of petals on the rose curve. When the coefficient of the theta is even, you actually have twice as many petals as you do that number right there. So what this is going to look like is goes up like that, down, around, and this is actually the order in which the graph would travel. So when theta equals 0, r is 0. And then when theta equals pi over 2, okay, theta equals pi over 2, r is 0 again. So when I told you about the tangent lines to the other graph, now that you're in calculus, this is going to be more important. When theta equals pi over 2, that line theta equals pi over 2 is tangent to the graph at the pole, and the line theta equals, you can call it pi or 0 even, is tangent to the graph at the pole as well. R equals 2, similar to just y equals some constant. The r remains constant, and the r equaling 2, no matter what the angle is, the r is 2. And I actually started here, but I should have started right here. Theta equals 0, r is 2. Theta equals everything from 0 to 2 pi, r equals 2, and then you can keep going around and around. Graph won't change. Now, theta equaling pi over 3, the line pi over 3 means that no matter what the r is, the theta will still be pi over 3. And so we get two special cases of polar graphs, and those are the two special cases. So there you go. It's good to just memorize those. Now, finally, we have it's kind of how we ended the school year in Pre-Calc Honors. But anyway, I'm just going to pick random values for these points in which f prime is equal to 0. So let's say f prime is equal to 0 at x equals -4, 0, 4, and 8. Just so I can have real numbers. It's not going to change the shape of my graph at all. But if I think about what I did back when I was graphing, if I had f of x and I found f prime and I found where f prime was equal to 0, what I did is I made an f prime chart. So if I make an f prime chart here based on the information that I see on the graph, it'll be easier for me to plot the graph of f of x. Okay? So we always want the graph of f of x once we find what f prime is doing, and so f prime is equal to 0 again at these 4 values. Okay? Well, what's f prime to the left of -4? Well, f prime to the left of -4 is positive. It's negative in between, then positive, then negative, and then positive again. Therefore, f is increasing, decreasing, increasing, decreasing, and then increasing. And I'm going fast because I have 30 more seconds. So 0, 0 is where it says we want f to go through. We know we have a horizontal tangent line there. We have a horizontal tangent line when x is equal to -4, 4, and 8. So horizontal tangent line, if f of x goes up and then down, and then up, and then down, and then up, then we'd have horizontal tangent lines everywhere. It says we have horizontal tangent lines. And there we go.